Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step one aside as we jump into section 5.2 in the Big Ideas Math Integrated Math 1 textbook. We're solving systems of equations using the substitution method. It's an algebraic method as opposed to section 5.1 where we solved graphically. Now we're going to only kind of look at the algebra, and they might show some graph things here or there, but otherwise, algebra only. Now, with this, I guess we can have some decimal answers. I don't know if we'll have them or not. That being said, when we get our answers, we'll still write them as an ordered pair unless it's in some sort of word problem. We have 35 questions to do in total. Jump to the description section down below to find the PDF of that set and the timestamps for those problems. But of course, I'm going to begin with the lecture portion. Now, as I've stated in the 5.1 video, if you heard it, from here on out, I'm only, like when I do equation manipulation, subtract 4x from both sides, things like that, I'm no longer going to be showing the actions. I'm just going to go straight from one step to the next, just for efficiency's sake. So without further ado, I'm going to go ahead and get started. We're going to solve using something called substitution. Section 5.3 will use another algebraic method called elimination. We'll get there when we do. For now, substitution. And use them to solve real-life problems, word problems, that same kind of thing. Previous terms are here. Substitution method is something we've done in the past, right? If x equals 4, 4 takes x's place, that kind of thing. But now we're going to use probably bigger expressions. So use parentheses. Use those parentheses. Okay, another way to solve outside of graphing is using substitution. So here's what you're going to do. Solve one of the variables, solve one of the equations for one of the variables. That means get y by itself or x by itself. Now, that might have x on the other side of the equation when it says y equals, or it might have y on the other side of the equation when it says x equals, and that's okay. Our goal is to substitute into the other equation and solve for the other variable, because the idea here is when you substitute, let's say y equals something, and with an x in it, and you replace it with the y in the other equation, now that equation will only have x's in it. And they work in the same system. So whatever that x would have represented in the first one should be represented in the second one. When you solve for the first variable, you can now substitute that value into one of the original equations and solve for the other variable. Give me 1 second. Sorry, I had a timely message I had to respond to there. Okay. I think I mentioned all this stuff here. Let's jump into the example. Let's see what they do, and we'll follow suit. Solve the system of linear equations by substitution, not graphing. And I'm probably glad I'm not graphing something like this bottom one here. Y equals negative 2x minus 9 and 6x minus 5. Y equals negative 19. Okay, they did some of the good work for you in the problem setup. Y is already by itself in the top equation. If y equals negative 2x minus 9, that means negative 2x minus 9 can take y's place in any other equation in the system. So I can substitute for y right here with negative 2x minus 9. Just like if y just equaled negative 9, right? It would just take y's place. It's just a straight substitution. So what are they going to do? Take the bottom equation, substitute negative 2x minus 9 for y. Notice it's in parentheses because it's multiplying by negative 5. And then we solve. Now, they're doing a lot of the important things you'd have to make sure to take care of in this one example, because you are distributing a negative 5 into these. They turn positive and all that stuff. So it's really important that we check on that and it still works out. Now, notice though, this is just an equation with one variable in it now. Before it was an equation with two variables. Couldn't find out what x or y was alone. But now that it just has x in it, we can solve. You combine like terms, you get x on one side of the equation, you divide, you get x equals negative 4. So in our system, and remember our system needs both x and y in it, we found the x value, the solution to the system. Now, what do they do after that? They did mention you can substitute into either original equation and solve. You can technically substitute into any equation that you have as long as it solves for y, but you probably want to do it in an original and make sure all the work is right. That being said, I would recommend you do it in the one where y is already solved for, and they're going to do the same thing. You know where y equals negative 2x minus 9? Yeah, plug in negative 4 in for x right there. It's a perfect place to do substitution because y equals y equals y equals. So y equals negative 1, and that's where you have your solution set, negative 4, negative 1. Now, mind you, even though we're not graphing it, that doesn't mean that these couldn't be graphed and intersect at this place. The solution is still an ordered pair. We will not stop writing ordered pairs for these. Now, they did a double check in both equations here. I don't know if I'm going to be doing that unless it's like a requirement or I want to mention it the first time. But you see the left side equals the right side by substituting negative 1 for y, negative 4 for x, negative 4 for x, negative 1 for y. You get negative 19 equals negative 19. it all works out. That's a solution without the graphing needed. And again, I'm glad I didn't graph this one. This would have been a really awkward bottom graph to do, and I don't know, I guess it's inside your window range, but yeah, I wouldn't have really loved to do that one, so it's good that we had another algebraic method to solve using that. Now, was that the only method to do by getting that y and substituting there? No. Strategically, is it the most optimal? Absolutely. There are times where we're going to talk about strategy, and if the book doesn't talk about it, I will. But we talk strategy and which variable you should get by itself, by which one has the least amount of steps to get by itself, which one has the least amount of negatives, but most importantly, which one has the least amount of fractions, or in hopefully all cases, no fractions somewhere. So that's what we're probably going to get into as we move forward. Because as you could tell, y was already by itself in this equation. That's not always going to be the case in these problems. Although in those problems, that's when substitution is the best method to probably do. Okay, here's an example where nothing is by itself. It says solve using substitution, and so what we want to do is get a variable by itself. It says you could begin by solving for x in equation 1, solving for y in equation 2, or solving x in equation 2. Now notice they never said solving for, oh yeah, never mind. So we are going to solve for y in equation 1. They're going to add x to both sides, boom, and they get y by itself. And you could solve for any of the other three variables here. Now, it's not the worst thing if I solve for y in this bottom equation. I subtract 3x from both sides. It took one step, and there are no fractions. It did leave us with negatives, so it's not the best one either. I think I like this one most like they did. All positives, one step, all good to go. Getting x by itself on this one would have taken 2 steps and switching some signs around, so it still would have worked. Maybe not the best one. This x I would never really want to get by itself, because what ultimately would I have to do? Divide everything by 3. And it's no problem if other numbers could divide by 3, but 1 can't divide by 3 and -1 can't divide by 3. So when they're not divisible by 3, that means fractions will be ahead, and I don't want to substitute that and get fractions. So do I want to get this x by itself? No. They got this top y by itself by adding x to both sides. That's a good one. Now we take this expression and we'll substitute it for y in the other equation. You want to use the other equation to get what else y is expressed in terms of with the x's and stuff to make them equal, and then you could actually uniquely get a certain solution for x instead of getting just the left side to cancel out with the right side. So you substitute there, and you still use parentheses. I mean, there's nothing doing there. They combine like terms, they subtract 3, they divide both sides by 4, they get x equals -1. Now, they substituted back in an original equation. I actually won't do that in a scenario like this. I'm going to substitute it back in the one where I got y by itself. I'm going to trust what I did there was fine. They did it here, but notice I can do -1 plus 3 and I get 2 for y. They got 2 for y. All's good. X is -1, y is 2, ordered pairs -1, 2. They double check, left side equals right side. They even show when they graph that they intersect in the same place. Not that we have to do that, or maybe we do, I don't know. But that's still the substitution method. So guys, substitution method's all about taking an expression, substituting for your variable in something that's equivalent to it, and then solving for the other variable and using that solution to solve for the first variable. All right, solving real life problems. Yeah, they have real life problems, I'll tell you what. A drama club earns $1,040 from a production. A total of 64 adult tickets and 132 student tickets are sold. An adult ticket costs twice as much as a student ticket. Write a system of linear equations to represent the situation. What is the price of each type of ticket? Okay. If you did the graphing ones with me, it's the same kind of thing. We're creating our own equations. Now, this time they didn't do something that totals to number of tickets, something that totals to number of costs. They actually did a cost amount, but then they did a comparison one. An adult ticket costs twice as much as a student ticket. Now, do we have to use x and y in these? This time we don't probably have to use x and y. And I'll tell you why we had to for graphing and why we don't have to here. For graphing, we had to graph it, right? X, y, and so it makes a lot more sense. I think you'll feel more comfortable where I have my slope, my y-intercept here and things like that. I want to use x and y for those ones. For these ones, we don't have to use x and y because number one, we're not graphing, but number two, as a word problem, our answer doesn't need to be an ordered pair. We're going to say how much each type of ticket costs. A student ticket costs this much, an adult ticket costs this much. So you could do something like A for adult ticket and S for student ticket. Why might not I use that? Because I don't like using S's, because S's look like 5s, or at least my S's look like 5s. So I'm probably not going to use that. Looks like they're going to use X and Y, so hey, let's use X and Y. But when you do that, define your variables. So looks like their adult ticket value price is X, and their student ticket values y. They have two equations. 64 adult tickets times the cost of each ticket is the amount of money from those tickets. 132 student tickets times the cost of each student ticket is total amount of student ticket dollars. And they add up to $1,040. The other one is the adult ticket price is twice as much as the student ticket price. That means you'd have to double student ticket price to match adult ticket price. So this is your system here. Boom and boom. Just make sure you define your variables so you know when you solve what you get. Now, considering x is by itself in this equation, we can take 2y and substitute it for our x in the top equation and solve for y. When you do, you get y equals 4, and then take that y, substitute it back in that equation. 2 times 4 is 8. So this 4 and this 8 were not how many adult tickets and student tickets, but the cost of each. Each adult ticket costs $8. Each student ticket costs $4. This is how you want to write our final answer. Ordered pair doesn't really matter this time for word problems. And that's where I might use different variables if I feel that they can start with the word and not look like a number, like an S looks like a 5 for me. That's really the only word problem with me. 2's can look like Z's, 1's can look like L's. O's can look like zeros. T's can look like pluses, okay? But I can generally make those look better. Maybe not the O's and zeros and the S's and 5s. So anything else I should be good. Hey guys, that's the end of the lecture portion there. Those go relatively fast as long as we're good on the algebra things. Let's look at the vocabulary and core concept check, and then we have up to number 35 to complete. Number 1 on writing, describe how to solve a system of linear equations, by substitution. Well, I'll write what I can here, but isolate a variable in one equation, substitute for that variable, substitute the expression for that variable in the other equation, variablation, that's a word, in the other equation, solve for the second variable, and sub its solution to solve the first variable. So let's say the first variable, let's say you isolate x in an equation. You got to say x equals something with y. Take that expression, substitute it for x in the other equation, so now that other equation has y's in it, solve for y. That's the second variable. Now sub that y equals, say it's y equals 3, substitute that 3 into one of the original equations, or the one where it says x equals, and solve for x. And write your final solution as an ordered pair for non-contextual problems. For contextual word problems, write out answers with units. Number 2, when solving a system of linear equations by substitution, how do you decide which variable to solve for in step 1? So they're talking strategy here as well. They didn't mouth all the strategic things before, but for me, I'm going to solve for the variable that would require the least amount of steps, provide the most positive numbers, and have the least amount of fractions. Now, I'll tell you what, when push comes to shove and I have to prioritize which ones matter to me most, the least amount of fractions actually matters most to me. If I can get the least amount of fractions, by getting the least amount of fractions, I feel best on that set. Okay? So if that means it's going to take one more step on another thing to get that there, sorry, I'm trying to fit this in bold, but not shrink it and all that kind of stuff. Okay, that looks pretty good right there. If it means no fractions at the cost of anything else, more negatives, more steps to take to get it by itself versus any of the other ones, I'm going to do that. Okay, just keep that in mind. That's the best strategy thing for me. Less fractions, better. All right, guys, we're going to start with this problem set numbers 3 through 35. I don't know if we have to actually graph anything here or if we have to use the calculator, but let's go ahead and get started. Prep my slides here, and here we go. We're going to start with numbers 3 through 8. It says, tell which equation you would choose to solve for one of the variables explained. Okay, they're actually going right into the strategy stuff. And by the way, that means we're actually not solving these systems themselves. They're just saying, taking a look at this, which variable is best to you in terms of getting by itself, so when you do substitution, you're set to go. And I'll show you those steps I'm going to take to get there. These are things I'll actually do with my students often, where I'll say, would you rather get variable 1 by itself, variable 2 by itself, variable 3 by itself, or variable 4 by itself? Let's just talk shop and say which ones would make most sense here. Variable 1, getting that top x by itself is pretty nice. I subtract 4y over, it takes one step, there are no fractions, pretty good. The 4y is negative, that's not the worst thing, I just like more positives so I can deal with them. But subtracting 4y over, pretty fine. This variable 2, this top y, It's actually kind of bad. Not only are you have to take the 2 steps to get here, but you got to divide everything by 4. 30 divided by 4 is a fraction. 1 divided by 4 is a fraction. That's not a good one. I don't like that one at all. Variable 3 is great. Add 2y to both sides. It's positive, it's 1 step, it's 1 term. That's my favorite one probably. I really like variable 3. This equation would then just say x equals 2y. I love that one. Variable 4 would require subtracting the x and dividing by -2, which means 2 steps and a fraction. It's positive, but it's a fraction, so I don't like variable 4. Either variable 1 or 3 is good. I really like variable 3 the most, and that's what it would look like. Remember, we're not done. That means 2y would take x's place in this equation, but that is really the best one to me. I explained away why it is that I like that one, but basically the bottom x, I'm going to just call it variable 3. The bottom x in my system is the one that I like the most on that. Now, I'm not going to have massive discussions on all of these ones, guys. Hopefully, it's going to make a lot of sense what I'm doing with these ultimately. Number 4, 3x minus y equals 0, and 2x plus y equals -10. Once again, if I were comparing variables 1, 2, 3, and 4, off the bat, I don't love variables 1 or 3 on the x's because dividing by 2 or dividing by 3 somewhere leads to a fraction. Even if 10 divided by 2, and I know it's negative, I don't care about that part. Even if 10 divided by 2 or 0 divided by 3 isn't a fraction, these ones, these coefficients here dividing by 2 or 3 means a fraction. So I don't love those ones, or I'm already eliminating those. If I subtract 2x from both sides, that's 1 step there. That's pretty good. It gets the y by itself in 1 step, but they're both negative and it's 2 terms. Whereas here, I could either subtract 3x over, or heck, I could just add y over. That would be 1 step, right? Adding y over, this would become y equals 3x. Yeah, I add it to the right side, but now I write it on the left side. I really like variable 2, the top y the most there. 1 step, 1 term, just like you saw before. Loving that guy there. Let's just stick with that one. And if you're spending so long on trying to decide which one to do strategically between 2 that are viable, don't waste time on it. Just go to one of them and you'll be fine. No fractions is really the key to me. Now, does each problem always guarantee there will be no fractions? No. Will they give you problems with only no fractions? Maybe. I don't know. Maybe they're going to make them very nice for each of these problems. I can think of ones where it would take a little bit more time to do. Because right now what it looks like is find the one with a coefficient of 1 or -1. And right now I'm looking at this bottom y right here. I'm looking at the bottom y. Variable 1, the top x, I got to divide 3 and 11 by 5. No good. Divide these by 3, 5 and 11 by 3. No good. Divide 5 by 5 is fine. 1 by 5 is no good. Divide everything by -1 here or add the y over or whatever. By default, this one is the only one that has no fraction. So when push comes to shove, I add y to both sides and subtract both sides by 5. My equation will say y equals 5x minus 5. Now, this is the expression that goes in for y in the top equation, right? That's what we're going to do with it there. But that's how I get it by itself. That's the one I want to get by itself right there. So hopefully this is starting to make sense, and I won't over-explain it on the problems afterward because we're starting off with these. I do want to get into it here. Number 6, 3x minus 2y equals 19. X plus y equals 8. I'll be straight with you. Equations 1 and 2, if I consider the top one equations 1 and 2, don't love them. You get fractions. These ones here, honestly, it's an either-or proposition. I personally would rather get x by itself. The only reason why, because here's the thing, subtract x from both sides or subtract y from both sides. Mr. Robinson, they're both the same. Sort of. What I'm doing is I'm looking a little further into the problem and saying, I kind of like x more because when I substitute it, x equals 8 minus y, or negative y plus 8, whatever. When I substitute it, notice I'm substituting in a set, I'm plugging it in for x. That means it's going to be multiplying by 3. Positive 3. A distribution of a positive is preferred to a distribution of a negative. If I got y by itself, it'd be -2 times things there. Distributing a negative leads to more issues. So I personally prefer the x over the y. If I had to choose, they are almost equal. But if looking ahead, if I had to choose, I think I'd get the x by itself. The y is not bad at all, though. Number 7, x minus y equals -3. 4x plus 3y equals -5. I think we can dismiss the bottom two right now when it comes to multiple steps plus fractions to be had when you divide, so those are no good. 1 and 2, this is once again something where you can kind of make a choice. If you get the x by itself, let's take a look. If you get the x by itself, adding y over, you get y minus 3. Lovely. That's fine. If you get the y by itself, you can either subtract x and divide by -1 or add y and add 3. Take a look at this. Everything here is positive. So what do you prefer? All positives in 2 steps or with a negative in 1 step? I think most people just go with the 1-step one. This is a win-win, I'd say, on this one. Either or, you're good. I'm going to go for equation 1. Just, again, push comes to shove, flip a coin. Don't spend a long time thinking about it. Substituting into either of these leads to all positives anyway, or distributing a positive. So I don't think I care. But you can tell what I'm trying to do here, right? Now, again, none of these problems have you divide. Like, if you looked at this straight up, get the x by itself on the bottom, right? Just 1 step, that kind of stuff. So in that kind of situation, you can tell which one you want to get by itself. They're telegraphing it to you. There are other ones that are not as easy. Like, what if this said, here, I'm going to make this up for a second. What if this said 4x, da, da, da. Now, none of them have a coefficient of 1, and you make a choice. Honestly, I'd get this y by itself, because I could divide these all by 2. But this one's a 1x. It's a 1x, so you can tell this is the one that I'm going to want to get by itself here. These ones lead to fractions somewhere. Divide by 3, divide by 5. Icky, icky. But this one here, x doesn't have to divide by anything. It takes 1 step to go and add that 2y over here. So no good, no good. Divide by 2. Here's a fraction. No good. So my favorite one here, add the 2y over. You get x equals 2y minus 6. Even at the cost of a negative there and a distribution, whatever. That's going to be the go-to, that variable for sure, for sure. All good. Okay, numbers 9 through 16, we are going to solve by substitution. They do say check your solution. I'll probably do that mentally. Now, what we will do is look to get a variable by itself if it's not already, and if it is, we'll use that one for substitution's sake. What's interesting actually about this one is both of them are in some way isolated. So the question is, which one would you like to substitute for the other? I can either take 17 minus 4y and substitute for x here, or I can take x minus 2 and substitute for y here. My personal preference, I'd like to substitute for x in the bottom equation because I have nothing to distribute, and especially not a negative to distribute. So now I can rewrite this bottom equation with y in it, and it will say y equals, instead of x, I'm going to write 17 minus 4y, and there's a minus 2. Now I have a 4y on this side, or negative 4y I should say. Let's first combine these, then we'll get there. So 15 minus 4y. If I add 4y to both sides and divide both sides by 5, I get y equals 3. Keep in mind, I'm not showing the actions in between anymore. I've warned a couple times on that, so just get ready. Now we're going to substitute in for x this 3 for y. Not substitute for x, but substitute to solve for x. Right here, boom, like so. And probably organize your work better than I'm doing there, but as I'm visually showing you, 17 minus 12 is going to give us 5. So x equals 5, y equals 3. But our final solution, guys, will be an ordered pair, 5, 3. Don't stop doing the stuff that you would have done if you graphed these ones. The ordered pair is the solution set, 5, 3. They did say double check. 5 equals 17 minus 12. Well, we just saw that one, right? Literally. So let's just make sure this one works. 3 equals 5 minus 2. Yes, it does. All right, there's the double check. We move forward. Number 10. On number 10, y is actually by itself in both equations, which is an interesting way of seeing it. There was a, if you find one of my really old videos, and when I say really old, I mean maybe 8 years old or so, our textbook separated what was called substitution method from something else called the equal values method. I believe that was the name of the phrase, which said when the same variable is isolated in both equations, set those two parts equal to each other. Literally, they would, 6x minus 9 equals negative 3x. And that is what we do. Why? Because negative 3x is taking y's place in that equation. That's literally what it's going to look like. So, hey, it is the equal values method, but it's substitution. Now, that means I'm going to solve for x given this. I can add 3x to both sides, and I can add 9 to both sides. Be careful, this still is 0 until you add the 9 over. Divide by 9, you do get x equals 1. And in either equation, we can solve for y. Let's do it on the bottom equation with less work. Negative 3 times 1 is negative 3. There's the x, there's the y. We get 1 comma negative 3. I think you're automatically going to like substitution method more than, say, solve by graphing. Graphing takes a little more setup and things to do. Listen, it depends. Graphing has its pros and cons. I actually have somewhere I have a great pros and cons list of why we might want to solve using some methods versus others. Graphing does have its benefits for sure, especially when it comes to no solution and infinite number of solutions cases. We haven't seen those yet. I don't know if special cases actually pop up, but somewhere we might. Anyway, x and y here, what should we do? Well, a variable is already by itself. So this x right here, already solved for. So let's take the 16 minus 4y and substitute it for x. My favorite phrasing of this is, you take that expression and shove it up your x right there. So here it's going to be a substitution. We get 3 times here, 16 minus 4y plus this 4y equals 8. There's a distribution here, 3 times 16, 3 times negative 4y, like that. Negative 12y plus 4y combined to become negative 8y. And again, my algebra stuff I'm going to do is going to be a lot faster than it used to be, and I hope that's okay. I subtract 48 from both sides if this stays negative, and I divide both sides by negative 8. We'll get y equals 5. Now, I have an x by itself here. I'd recommend substituting the 5 for y in that equation. It's a lot faster. So 16 minus 4 times 5 is 16 minus 20, which is negative 4. So this final ordered pair is negative 4, 5. I don't believe I double checked the last problem. Let's just trust that it was okay. This one, if we double check, I don't need to really double check in the top equation because that's where I did the substitution. So let's do the bottom equation. We have negative 12 plus 20 when we substitute, and negative 12 plus 20 is 8, so that works. All right, number 12. On number 12, we have the y by itself in the bottom equation. So negative 5x plus 3y equals 51, and y equals 10x minus 8. So we'll substitute 10x minus 8 in for y in the top equation, in the other equation, and then you rewrite that equation with that in mind and solve for y. Solve for x, excuse me. Negative 5x plus 3 times y. Boom, y equals 51. We have a distribution of this 3 going on here. Combine like terms. And begin your solving stuff here. Add 24 to both sides, we get 75. Divide both sides by 25, 75 over 25 is 3. The y that we can solve for here is 10 times 3 minus 8, or 30 minus 8, which is 22. So final ordered pair is 322. Again, don't lose sight of what you actually write as your final answer there. Let's double check in the top equation because the bottom equation was taken care of with that. That's negative 15 plus 66. 66 minus 15 is 51, so that does work out. Number 13, I think 13 through 16 are the ones where, well, no one variable is yet isolated, so we have to do so. Now, this one is actually an interesting system because the top equation doesn't have y in it. That means, as much as we have that discussion on, hey, let's get a variable by itself, literally getting a variable by itself here, if we divide everything by 2, we've already solved for a thing. X equals 6, that's the x in your system. We're done on the x. We got to now solve for y given that, and the only place to do that, I guess, is in the bottom equation. Substitute 6 in for x there. So 6 minus 5y equals negative 29. If I subtract 6 from both sides and divide both sides by negative 5, we get a y value of 7. So your final ordered pair is 6, 7. There's really nothing I can double check there. The 6 I substituted in the bottom equation. The top equation doesn't have a y in it, so that must be it. I must be good. Now I'll tell you what. I never had this heavy emphasis of having my students double check in my equations. I know other teachers from students who I've tutored that have had them do that. And I'll tell you what, it's very, is it prosperous is the word? You're very well off in doing so. If you double check both. If you double check both equations, you're most likely to not get something wrong. Or when you find out something's wrong, you can now go back and check it. So I would recommend you do the double checks as often as you don't feel confident getting the algebra right. I feel confident myself. I'll do the mental versions where I can, but check both of them, right? It's solving the system, not solving for one equation. Make sure you're aware of that. Number 14 is a little more of the same. So I guess their buildup on this thing is getting a variable by itself, but in doing so, you're also solving for the variable. If I add 9 to both sides here, negative 1 plus 9 is 8. So this ends up being not only the solution for, it ends up being the solution for x. So although we'll substitute that expression in for x in the other equation, x is now already solved for as well. So we just need to solve for y. This is 16 minus y equals 23. It's one of the ones where I'd rather kind of add the y over here and then subtract the 23 over it, and I'll get -7. So y is -7, which means we have 8 comma -7. And again, one of those ones that double checking doesn't really do anything for me, assuming my math there was good, which it looks like it was, because there's no y in the bottom equation. Now, we did not graph. I'll tell you what, the lecture portion of section 5.1 did a graph with an x equals equation. Remember, it was a vertical line. We're not doing any graphs here, but x equals 8, guys, is a vertical line on 8 for x. Just remember that. Number 15 and 16 seems to be the ones that we would do kind of like questions 3 through 8. We are strategically trying to decide which variable to get by itself and then moving on from there. If I had to make a choice between any of my 4 variables here, it's either down to this bottom x or this bottom y. And honestly, I don't really seem to have much of a preference. No matter what, these are going to be negative. It takes one step to do. There will be no fractions. I guess distribute into the smaller set with this y. So subtract x over. Why not? We're going to have an equation that says y equals -x minus 3. Again, it's one of those things where you're better off not spending time trying to think about which one to do it with. You just go ahead and eventually do it. So there's the substitution right here, lads. We're going to do 5x plus 2 times that expression for y. Now we have to distribute the 2, -2x minus 6. And look, all the pain is over, right? It's done. The thing about negatives and all the bothersome part, it's done. We're done. Now we combine like terms. Add 6 over, 9 plus 6 is 15, and divide both sides by 3, you get x equals 5. And again, I want to stress how much faster and efficient I am without writing the plus 6 on both sides, divide both sides by 3. You got to make sure you're doing it right, and that's where the double check comes into play. That's probably also why I'm comfortable doing it here. Now, we haven't solved for y yet. I can use this equation. I know they like to use original equations, but I want to substitute just that 5 right here. -5 minus 3, that's -8. We'll do a double check on this, but our ordered pair is 5, -8. Again, top equation, or bottom equation, 5 plus -8 is -3. Cool. 5 times 5 is 25. 2 times -8 is -16. 25 minus 16 is 9. 9 equals 9. Works. Number 16. If you're looking at which variable to get by itself, which one would you recommend? Top x, top y, bottom x, or bottom y? Again, they're making some of the easier decisions for us by showing there's just an x by itself, meaning coefficient of 1 on that bottom equation. Let's get that x by itself, guys. Add 2y to both sides. We'll get x equals 2y minus 4. So 2y minus 4 is going to take x's place here, okay? Top equation. So now this top equation, instead of saying 11x, we'll say 11 times the quantity 2y minus 4. Minus 7y equals -14. And off to work you go. Distribution. Combine like terms. 22y minus 7y is 15y. Add 44 to both sides, and eventually you're going to look at 44 minus 14, which is 30. So 15y is 30, and divide by 15, you get y equals 2. The x value, again, we have an equation now with x by itself. And I've mentioned that, you know, hey, maybe 4 minus 4 is 0. Hey, maybe you're really liking substitution versus graphing. And I get it. Me too. Me too. I do. And I'm glad they're kind of doing substitution first, because here's the thing. You're going to learn the elimination method in section 4.3, and sometimes you're going to say, like, oh, I really like elimination method, though. But we're going to find means and times for when you should use substitution versus elimination. And this was kind of a pick and choose. You know, when you learn elimination, you'll kind of figure out what to do. But one thing about substitution that I really like is, once again, when you get a variable by itself, you can plug it into that one where it says x equals. Oh, you're well on your way to solving that other part. So I really like that part about substitution. Even elimination doesn't do that. All right, error analysis number 17. Describe and correct the error in solving for one of the variables in the linear system. Let's see what they did. We have this 5x minus y equals 4. Okay, so here's what they did. They got y by itself in the top equation. Not bad. And here's the thing. This is one where I wouldn't have actually minded getting the y by itself in this. It would take multiple steps, but you divide by 2, meaning there's no fraction. I'd most prefer this one. It's just here if I divide by 2 with 8 and 12, -12, at least there's no fraction. Anyway, They got the y by itself here. They even divided by -1, switched the signs. That's all good. And they did a substitution. What's the problem? They substituted back into the equation that they got y by itself in. Now, Mr. Robinson, I don't see a problem with that. Why do we have to do in the other equation? Well, look what happens. You have an identity here. You just get 4 equals 4. The variables cancel. 4 equals 4. Is it infinite number of solutions? No, you substituted back in the equation where you already have information. It doesn't work to find out answers that way, to just work with one equation. You need to work with both for the system. So they substituted an expression for y back into the equation they solved for y with. They need to substitute it into the other equation. You need to get more information out. Now, here's the thing, because I use this example a lot. Let's say, and I'll solve this one in a second, but let's say we had a word problem thing that said, hey, the number of boys and girls in a class is 30. All right, well, we can make an equation that says like b plus g equals 30, right? And then I ask the question, how many boys and girls are there in the class? How many boys are in the class? How many girls are in the class? Naturally, some people will say 15 and 15. Well, you don't know that for sure. It could be 20 and 10. It could be 30 and 0, right? We don't know. There are not an infinite set, but there's a massive set of different things. It could be 12 and 18, right? It could be 21 and 9. So we don't know. But if you rewrite this equation to get g by itself, the number of girls in the class is, you take away the boys from 30, right? Okay, I rewrote the equation, but if I substituted that into here for g, I didn't come up with new information. It's rewritten information. I would need another bit of information, such as there are 4 more boys than there are girls in the class. Girls is, well, if there are 4 more boys, I guess we have to do if there are 4 less girls. Like that. But anyway, you would need another bit of information to solve with, basically. We can't just use one bit of information, reword it, and be good. We need to do something else to solve. In which case, I guess that would be 17 boys and 13 girls. But anyway, we're not doing that problem. Let's continue on this one. I apologize for the tangent. Let's go ahead and finish this one up. So we have y equals 5x minus 4. Okay, that is a rewrite, and it's a proper rewrite of that first equation. That's fine. We have this other equation, though, that is 8x plus 2y equals -12 that has not yet been touched. This is where we have to do the substitution into that guy there. So now that equation will say 8x plus 2 times this y equals -12. Yeah, the boys and girls thing, I just wanted to make sure to stress why it is that doesn't make any sense to just rework that stuff right there, right? You have to get new information out from it. Now, this is an interesting solution set, unless I did something wrong. So far, it looks good. Like I said, I think their work on it's good. When I add 8 to both sides, I'm getting -4, and now I divide by 18. -4 over 18 reduces to -2/9. Hardly my most preferred answer here. It said correct the error. I don't know if they wanted us to keep doing the problem, but I'm getting -2/9 for x. Let me make sure I did it correctly because I was talking during that time. 8x plus 2y equals -12. I substituted for y because I want to make sure I didn't do it wrong. 10x minus 8 added combined. Yeah, it looks fine. And like I said, the original equation is fine. So we do a substitution there. We get x is -2/9. Now, no method that you choose is going to change what that answer is. So this is what you got to do, right? Or maybe elimination. I would not like to solve this one by graphing because I don't know how to approximate -2/9. Anyway, 5 times -2/9 is -10/9. -4 can be rewritten as -36/9, and that would give us -46 over 9 for y. So the final solution is -2/9 for x, -46/9 for y. You're almost like, well, I prefer the answer the error analysis thing got. I don't know if I made a mistake. It looks good. I don't want to double check. And yeah, we'll just leave it like that. So maybe we weren't supposed to actually solve, but there it is. Fraction answers, they happen. Number 18. Describe and correct the error in solving for one of the variables. So they get y by itself by subtracting 3x from both sides in this equation here. All's good. They even substitute for y in the other equation, 4x plus 2 times y equals 6. They distribute. All good. They combine like terms. They subtract 18 over. All good. They divide by -2. That looks good. I don't see a problem with that. 3x plus y equals 9. 3x plus... Well, that's dumb. They substituted 6 for y in this thing. No one's going to make that mistake. Sorry. When I said that's dumb, no one's going to make that mistake. There are plenty of other mistakes that people would make on this thing. But after solving for x, they substituted their value for y instead by accident. Or on purpose. They won't even check it. We have to substitute for x. Must substitute 6 for x into either equation and solve. Now, where do I personally prefer to substitute? You've heard me say it. You've seen me do it. I want to substitute 6 for x in one where y is already isolated, such as this equation here. Y equals 9 minus 3x. Now, we do have x equals 6. We solved that, right? Here's our substitution. Y equals 9 minus 3 times 6. So -9. Now, you can also tell that they made a mistake. Well, listen, they're not writing their answers as ordered pairs. I don't know what they're doing. I guess they can't because they're like, what happened? Did they? Oh, I put that check mark. They got x equals 6 and x equals 1. How did they get two different x answers in a linear system, right? That's not going to happen. Anyway, you should get an x, you should get a y, you should write it as an ordered pair. That's their other problem. They're not getting an ordered pair set. All right, number 19, modeling with mathematics. A farmer plants corn and wheat on an 180-acre farm. On a 180-acre farm. The farmer wants to plant 3 times as many acres of corn as wheat. Write a system of linear equations that represents this situation. How many acres of each crop should the farmer plant? Okay, I'm going to use, instead of x and y, let's use w and c. Let's let w equal number of acres of wheat. So acres of wheat. Hey, Brian, I want to plant some wheat and some corn. C equal acres of corn. The farmer wants to plant, let's see, farmer plants corn and wheat on a 180-acre farm. So the total number of acres of wheat and corn will be 180. But we also have a comparison of wheat and corn. Farmer wants to plant 3 times as many acres of corn as wheat. 3 times more corn than wheat. So the amount of corn equals 3 times the amount of wheat. Don't triple the amount of corn. The amount of corn is triple the amount of wheat. That's what we have. So there's our system. And let's solve. And I'm not going to write the final answer as an ordered pair. I'm going to state how many acres of wheat, how many acres of corn. We have C already isolated, so we'll substitute 3w for C in the top equation. It'll say w plus 3w equals 180. That's 4w equals 180. And when you divide by 4, you get w equals 45. That is 45 acres of wheat. We'll get into that. C is 3 times 45, 3w, which is 135. 135 plus 45 indeed is 180. So that seems to check out. Now, instead of an ordered pair, again, the farmer should plant 45, not 36, 45 acres of wheat and 135 acres of corn, which is triple the amount, right? If you do write the other one incorrectly, you would end up seeing, oh my gosh, I have 3 times more wheat than corn. That's not what we wanted. We wanted 3 times more corn than wheat. So there's that. Oh, Brian, I want wheatins. Number 20, modeling with mathematics. A company that offers tubing trips down a river rents tubes for a person to use and cooler tubes to carry. Oh, I see. I thought that they meant like, dude, that's so cool. And cooler tubes to carry food and water. I think that means to like stick in a cooler. A group spends $270 to rent a total of 15 tubes. Write a system of linear equations that represents this situation. So let's see. Tubes for a person to use. So there are 2 types of tubes. There's normal tube and cooler tube. Let's see. They say a 1-person tube and a cooler tube. I'm trying to think. I guess I'll just call them X and Y this time because I don't really know what we're differentiating just yet here. So let X equals, let Y equals. But let's define our variables. Let's do that. Company tubing trips down a river for a person to use. Oh, I see. The cooler tube doesn't carry people. So there's the one-person tube. How many of each type? Number of one-person tubes. And then C is number of cooler tubes. I gotcha. I was trying to determine based on the picture. And they have to quote cooler instead of using it as like a way to describe the kind of tube, like it's so cool. It's a cooler tube. Okay, so what's the information here? 15 tubes total. Number of one-person tubes, number of cooler tubes in total is 15. Now, there's information on the bottom if you see this. A one-person tube is $20 for rental. A cooler tube is $12.50 per rental. So when you spend the amount of money on one-person tubes and cooler tubes, and I'm just going to write 12.5C, that equals $270. Now, in terms of getting a variable by itself, I'm probably going to get P by itself on the top. I don't want to distribute something that's going to lead to more decimal work, so I'll just leave it right there. So P equals 15 minus C. We'll substitute 15 minus C for P in the bottom equation. So we'll have 20 times 15 minus C plus 12.5C equals 270. Now, if you don't want to deal with the fraction, I get it. Ultimately, it's just a division you can use in your calculator anyway. I don't think it's really going to get in the way of the answer. It's up to you, though. However, if you do get rid of it, you have to get rid of it by, say, multiplying everything by 2 or by 10 or something like that. Anyway, let's distribute. 20 times 15 is 300. And then minus 20C plus 12.5C equals 270. Yeah, that's negative 7.5C, I believe. I'm going to add 7.5C over. I'm sick of dealing with negatives and decimals. Subtract 270 over, I get 30. And that's actually 4. I know that one in my head. So C is 4, and it should be a whole number answer, right? You can't 4.5 or something like that, cooler tubes. So that's C equals 4. P is 15 minus C. So P equals 15 minus 4, which is 11. Right? The whole idea was the combination of them. They add to 15, and listen, that cost I think should be $270. So the group rents 11 one-person tubes and 4 cooler tubes, bro. Just like that. Okay. Numbers 21 to 24 say, write a system of linear equations that has the ordered pair as its solution. Oh, that's weird. So it's like an open-ended set. You know, I've never really done that. You just have to make some things up. You make something up that works, right? If you want to use like a slope-intercept form, or like I can use a standard form one, x plus y equals 8. Because 3 plus 5 is 8, right? I mean, yeah, you could do it really easily this way. Hold on. You know, I never changed. If you've heard that before, it's the same time of day that this happens. I never got rid of that alarm, and I don't need it for anything. You just got to do things that just work, right? If I said 3x, that'd be 3 times 3, right? 9, right? Minus 5y, minus 25. So 9 minus 25 is negative 16, right? So boom. There's the system. As long as it's something that, make sure it's a distinct equation from that other one, that'll work. That's good. That's my answer. It's open-ended. These are open-ended things. Write a system. So let's keep working that out. I want to use some in slope-intercept form, things like that as well. So let's try that. So number 22, I could do something like, so for negative 2, 8, let's make a system that says y equals, remember that's 8, y equals, if x was negative 2 plus what is 8? Negative 2 plus 10. So y equals x plus 10. We can do that. I could do another one that's y equals, and let's change the x around. Let's call it negative 4x. So negative 4 times negative 2 is 8. I didn't mean to do that. But plus 0 would be 8. So that works as the other one. Right? So you can do different things like that, just arrangements of them. It's kind of up to you. Let's do mix and match of slope-intercept form and standard form. So number 23. These are Weird. I guess here we're kind of just using the idea of plugging these numbers in to make them work. They have to work for both equations. Right? So let's do y equals for one of them, slope-intercept form. Let's do like 3x. Oh no, because that is that. Let's do something different. Let's do like 6x. Y equals 6x. So 6 times -4 is -24, and we have to add 12 to get -12. So there's one of them. Now let's do like one of these ones. Let's do like 2x, which is -8. Let's turn these positive. 2x minus 7y. Oh, that's big. Plus 84. So -8 plus 84 is 76. So I guess like that, right? All right, number 24. 15 and -25. Well, those are big in and of themselves. So 15, -25. This time let's get x by itself. Let's do an x equals equation. They don't have to be slope-intercept form. So 15, let's do -2y. Let's do a -2y. -25 times -2 is 50. So we have to have a -35 there. All right, let's do -2y minus 35. 50 minus 35 is 15, so all of that one. And then let's go standard form on this one. Let's go x, I don't know, just x minus y. How about that? 15 minus -25 is 40. So boom. Boom, 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 boom. Okay. All right. Those are different. Numbers 25 and 26 are on problem solving. A math test is worth 100 points and has 38 problems. Each problem is worth either 5 points or 2 points. How many problems of each point value are on the test? This is one where I don't know what to start them off with other than x and y, but there's a number of 5-point questions. 5-point questions. And number of 2-point questions. So they have value, and that value is also the way that they're defined, right? So first of all, the number of questions there are 38 of them, or problems. There are 38 problems. X plus y is 38. Now the number of 5-point questions are valued at 5 points each. So each time you get one, multiply by 5, and then 2-point questions multiply by 2. In total, it adds to 100. So that's our system. Neither of them have anything solved for yet. Let's get a variable solved for. How about the y on top? And this will say y equals, say, 38 minus x. So now we can substitute 38 minus x in for y in the bottom equation. And distribute. You can see I did it with the bottom, with the 2. I'd rather do 2 times 38 than 5 times 38. So minus 2x equals 100. 5x minus 2x is 3x. Subtract 76 from both sides, you get 24. That's a 3x there. 3x equals 24, and divided by 3, you get x equals 8. X equals 8. Y is 38 minus x. 38 minus 8, and that's 30. That means there are 8 questions worth 5 points each, and 30 questions worth 2 points each. The test has 8 5-point questions and 30. Let's see. I kind of want to write the 8 as this thing here. 8 5-point questions. I don't want to write them both as that. Questions and 30 2-point questions. Okay. See, we do this for like basketball. Like, oh, you made this many baskets and then this many 3-pointers, this many 2-pointers. You could do things like that for these. Of course, I'll let them do the problems. All right, number 26. An investor owns shares of stock A and stock B. The investor owns a total of 200 shares with a total value of $4,000. How many shares of each stock does the investor own? So that's the price per share on the bottom. So we know the price per share. We don't know how many shares of each, right? Now they already have A and B as the variables, so let's use them. A and B is number of shares of stock A. And number of shares of stock B. Number of stock B shares. All right, 2 different equations. How many shares total? 200. We add A and B, and we get a total of 200 shares. And their value, 950, 9.5 per share times the number of shares, plus 27 per share times the number of shares here is 4,000. This is one of those times where I almost feel I don't want to work with a decimal very long. That's okay. We'll do that. Let's not deal with the decimal right now if we don't have to, though. So let's solve for B in the top equation by subtracting A. B is 200 minus A. My back's bothering me tonight, sorry. If I keep kind of like arching and stuff. Back issues tonight. So 9.5A plus 27 times this B equals 4,000. That's 54 with a couple zeros. Minus 27. Oh, 27A. All right. 9.5 minus 27 is 17.5. Negative 17.5. I'm going to add 17.5 to both sides, 17.5a, subtract 4,000 from both sides. Divide both sides by 17.5. If I told you I knew that answer, I'd be lying. It's going to be less than 100. I don't know. I'm going to use the calculator. 1,400 divided from 10.5. 80. A equals 80. They own 80 shares of stock A. How many of stock B? Well, 200 minus A. B is 200 minus A equals 120. So this investor owns 80 shares of stock A and 120 shares of stock B. Hopefully it's GameStop and like AMC or something. Okay. This is recorded in mid-2024. Let it be known that I was not wrong. I was early. Okay. Especially GameStop. Okay, numbers 27 and 28. Write an equation that represents the sum of the angle measures of the triangle and use your equation and the equation shown to find the values of x and y. So, I don't know if you know this, but the angle measures of a triangle add to 180 degrees. Maybe it's something they're supposed to have you know. This isn't geometry quite yet here. Let's copy and paste that. Actually, I don't really need to. Just keep it over there. So, x, y, and the 90-degree angle total add to 180. Soon you'll learn, like, look, if I subtract 90 over, let's make it slightly easier. If I subtract 90 over, soon you'll learn that the two non-right angles, the two acute angles in a right triangle, also add to 90. Anyway, there's one equation. Now, the other equation that we have in the system is x plus 2 equals 3y. Neither of these have a variable isolated just yet, and it doesn't really matter which one here. I could get the top y by itself, the top x by itself, or the bottom x by itself. Let's do the, I don't know why I'm overthinking this. Let's do the top x, so we don't have to distribute a thing here. X equals 90 minus y, and let's substitute in the bottom equation. So now I have 90 minus y plus 2. Equals 3y. If I add y to both sides here, I'll get 4y, and I have that 90 plus 2, which is 92. Divide both sides by 4, and you get y equals 23. 23. So x is 90 minus y, and I think it's 67. So these are the values of x and y. Now, these would technically be like the degree values, right? That's what we'd be getting there. So 67 degrees and 23 degrees. And if you assume these were drawn to scale, those actually look pretty decent for those. Now, I'm not putting degrees because they already have the degree symbol for them. So we're good. All right. Same thing here as far as the angles adding to 180. All angles in a triangle always add to 180, period. So we have the top, the initial one. I can write y minus 18. That's an angle. Plus y plus x. That all adds to 180. I'm going to do a little bit of rewriting. Let's write the x first. I'm a little particular that way. Y plus y is 2y. If I add the 18 over, I get 198. So I'm doing a little bit of house cleaning just to get a good standard form look. And then we also have 3x minus 5y equals negative 22. Once again, getting that top x by itself makes the most sense strategically. One step, no fractions. So let's substitute 198 minus 2y in the bottom equation for x. This will lead to a little bit of big numbers. So I get negative 22, like that. I got to distribute this 3. 3 times 200 is 600. Minus 6 is 594. 594 minus 6y, in case you were wondering how I do that math in my head. Negative 6y minus 5y is negative 11y. Let's add the 11y over. Add the 22 over. That's 616. Divide both sides by 11. $56. You get y equals 56. I'm glad it's an integer. It always makes me feel better that I probably didn't do anything wrong there. X, you can see right there, 198 minus 2y. X is 198 minus 2 times 56, which is 198 minus 112, which is 86. X is 86. And again, these aren't ordered pairs here, right? These aren't graphed, so these are still contextual. Not fully, but they are, right? So they're not really ordered pairs, because, and also here's the thing, right? They don't have to use x and y in those situations. It's not really in the graphed kind of way. All right, number 29, reasoning. Find the values of a and b so that the solution of the linear system is negative 9, 1. Okay, interesting. So here we have ax plus by equals negative 31, and we have ax minus by equals negative 41. So we have the solution as negative 9, 1. What we need to do here is substitute negative 9 for x and 1 for y. So the top equation will now instead say negative 9 times a, negative 9a, and then plus 1 times b, plus b, equals negative 31. So we're still solving a system. We're just not solving for x and y anymore. Now we're solving for a and b. And negative 9 times a here, and then minus b. If we had a chance to use elimination method, I would have loved to use it for this problem. Anyway, for this one here, I would love to get, I guess, the top b by itself. So let's, I don't know why I color-coded this, but let's go ahead and add 9a to both sides. B is 9a minus 31. So let's solve for b here. Now keep in mind, when we substitute this in for b to the bottom equation, that's minus and then parentheses here, 9a minus 31, something that people often forget. So that's a distribution of this negative 9a minus 9a plus 31. Boom, like that. These don't cancel. In fact, that's negative 18a. We will subtract 31 from both sides and divide by negative 18. That's 4. A is 4. So the a value that works out there is 4. And remember, this is not an ordered pair either. We're finding the a and b that would make this what it's supposed to be. I'll rewrite the equation as it is. But b is 9a minus 31. So b is 9 times 4 minus 31. 36 minus 31 is 5. So a is 4, b equals 5. That means the equations would have looked like 4x plus 5y equals negative 31 and 4x minus 5y equals negative 41. Apparently, negative 9 and 1 are the solutions to that set there. But these are the answers. Okay. Supposedly, that's reasoning. Number 30, making an argument. Your friend says that given a linear system with an equation of a horizontal line and an equation of a vertical line, you cannot solve the system by substitution. Is your friend correct? Explain. Okay. I guess your friend's correct, but your system is solved. So here's what they mean. What does a horizontal line look like? Horizontal line, for example, is like y equals negative 3. And a vertical line, for example, is like x equals 4. Okay. When it comes to the substitution method, once a variable is by itself, it takes place of the variable in the other equation, and you solve for the other variable. Okay, there's no x in that equation, so you can't sub. There's no y equation, you can't sub, but that's the solution. Guys, what's the solution in the system? The solution is 4, -3. Did I use the substitution method? No, because nothing substitutes, nothing plugs into the other thing, so I don't know how to answer whether we're saying your friend's correct or not. This is an example, by the way. Example of what I'm just referring to here. Is your friend correct? I guess, because you're not substituting. So if the substitution method requires it takes place of the variable in the other thing, my friend is correct because no substitution takes place. However, there is no work to be had. To be hard. It's not that hard. The solutions are the x and y that are present in their own equations. Because they did say vertical and horizontal line. And that's an x equals equation and y equals equation. So that's kind of a weird thing. I don't know how to answer that. I hope that's right the way that I stated it. Number 31, open-ended. Write a system of linear equations in which 3, -5 is a solution of equation 1, but not a solution of equation 2, and -1, 7 is a solution of the system. Oh, okay. So here's what we should do. Let's take the 2 points 3, -5, and -1, 7. Let's find the equation that's specifically for this pair of points. Write an equation out of that one and make that one of the equations. Then we have to make sure that -1, 7 works only for the second equation, but not the first pair of points. So, okay, let's first come up with the equation for this one. This was all part of chapter 4 stuff, right? So let's find the slope. So we got a rise over run, or in this case, a fall over run. That'll be -12 over 4, or -3. If I use the point slope form, just revisiting that, I could say y minus y1 equals m times x minus x1. And remember, we're not showing any extra steps here, or any extra actions. -3x plus 9, subtract 5 over, you get -3x minus 4. Okay, so this, or plus 4. So -3x plus 4 is one of the equations. This is the solution to both. Solution to, excuse me, that's just one equation. That is our equation number 1. This is equation number 1. Now, my equation number 2 can only be a solution, can only have, my equation 2 can only have -1, 7 be a solution of it. And it has to be unique to this one. So I could do literally -1 plus 7 equals 6. Right? Like x plus y equals 6. -1 plus 7 equals 6. So I could do something like that right there. As 3 plus -5. 3 minus 5 is not 6. So this can be equation number 2. So my system can look like these two here. Okay, interesting. Now, it was open-ended as far as this equation goes. This equation was not open-ended. I mean, the way that I write it is up to me. I could have written it in standard form. I could have written point slope form, whatever. I wrote slope-intercept form. This equation has no other interpretation. These points only apply for that equation. This one could have been anything I wanted as long as -1 and 7 worked and 3 and -5 didn't. And that's one of them. All right, number 32. How do you see it? The graphs of two linear equations are shown. So this is kind of like solving by graphing, but it's not quite. At what point do the lines appear to intersect? Well, they appear to intersect at 4, 5. I've got to get my eyes checked here a little bit, but yeah, there it is. 4, 5. Part B, could you solve it by substitution to check your answer in part A? Explain. Yes. Do they want me to solve? Because they said, could I? Yes. We could solve using substitution. Because it's a system of equations. I don't know. I don't really know what I should be saying for that one. I can solve because it's a system of equations. I don't know. Okay, guys, I'm gonna solve it just to kind of be there. I got y equals x plus 1 and y equals 6 minus 1/4 x. Here's the thing. Equal values method in play. Set one equal to the other because they're both y's. Listen, I don't like the fraction, so I'm going to multiply everything by 4. Now, I am going to show you the times 4 like that. I don't want you to be confused. So that's 4x plus 4 equals 24 minus x. Now I'm going to add x over, subtract 4 over, divide by 5. You get x equals 4. Y is x plus 1. Y is 4 plus 1. Y is 5. And that is 4, 5. Could I do it? Yes. How do I know? Because I just did it, homie. It's done. 4, 5. Did I get? Yeah, 4, 5. Okay. All right. Number 33, repeated reasoning. A radio station plays a total of 272 pop, rock, and hip-hop songs during a day. The number of pop songs is 3 times the number of rock songs. The number of hip-hop songs is 32 more than the number of rock songs. How many of each type does the song radio station play? Okay, that's 3 variables. So, unless, can I represent them as 2? Let's do pop, rock, hip-hop. P, number of pop songs. R, number of rock songs. Hopefully they did mostly rock songs. H, number of hip-hop songs. Hopefully it was 272 rock songs and none of the others. Sorry if I alienated myself from my audience with that. I don't care for pop. Pop's fine. I don't care about hip-hop. All right. So the total number P, R, and H equals 272. Now this is interesting because this is a system of 3, and you're gonna have 3 equations here as well. It says the number of pop songs is 3 times the number of rock songs. Oh, well, that already is shameful. Number of pop songs is 3 times the number of rock songs. The number of hip hop songs is 32 more than the number of rock songs. Why is rock the lowest? I know why, but 32 more than the number of rock songs. All right, there's our system. Now here's the cool part. I can solve for the rock songs first here. I can substitute 3R for P. I can substitute R plus 32 for H, and R can be R, so I can have an equation with only R in it and then solve for R first. So instead of writing P, I can write 3R. I got this 1R here, and then here I got, instead of H, R plus 32, and this equals 272. 3R plus R is 5R. Subtract 32 from both sides, and divide by 5. You get 48. 48. So 48 rock songs. To solve for P and R, pretty straightforward. You just substitute. You got 48 there. So P is 3 times 48. Ugh, it's too many. Is 144? 144? And H is 48 plus 32, which is 80. So 48, 144, and 80 is what we can say for those. So how did the radio station play? Let me make sure I wrote those for the correct ones. 144 pop songs, 48 rock songs. Yeah. Okay. There it is. Number 34. You have $2.65 in coins. Write a system of equations that represents this situation. Use variables to represent the number of each type of coin. I'm going to try and just limit it to 2 types of coins in total. Let's just use like nickels and dimes. Use a system equation to represent the situation. Let me type more of this. Like, so you have $2.65 in coins. I want to do one that like it works though. So hold on. Okay, I'm not going to type anything out from that. From nickels and dimes, you can add to 265, right? That's fine. So I can say, now the value of each dime, nickels and dimes, D is number of dimes, N is number of nickels. Okay. Here's the thing. Is nickels LES or ELS? It doesn't matter. I think it might be ELS, but that's okay. I want to look it up. Nickels, dimes. Yeah, it's ELS. I might be thinking of the element nickel. That might be LE, or maybe not at all. Maybe there's no LES. Okay, anyway. 10 cents per dime. Do I put 10 times D? It depends. We're talking about $2.65 in terms of dollars. $2.65. I have to put $0.1, $0.10, right? And 0.05 times the number of nickels. That would be an appropriate value amount. You can multiply it all by 100. Do 10D plus 5N equals 265. Now that's a cents unit stuff, and that's fine. Now let's make $2.65 out of this. Let's keep it simple. Let's do 20 dimes. That's $2. So I have 20 dimes as my number of dimes, and 65 cents worth of nickels would be, I think, 13. 13 times 5 is 65. So N is number of nickels, and so 20 plus 13 is 33. So that would be a system of equations that would work itself out there. Use variables to represent the number of each type of coin. So that's what I'm doing there. I'm going to make it up like that. There we go. Now, like I stated, you could also rewrite that top equation as 10D plus 5N equals 265 like that, and it works itself out. You can, of course, do things with quarters. That's all up to you. I did nickels and dimes. Probably should have done quarters because I know how to spell quarters. And that was not number 24. I don't know how to spell 34. 34 is with a 3, not with a 2. Okay, and the last question is number 35 on number sense. The sum of the digits... Sorry, I was making sure I wrote 35 here. All right, the sum of the digits of a 2-digit number is 11. When the digits are reversed, the number increases by 27. Find the original number. All right, I've done these kinds of problems before. All right, let's let x be the original tens digit. And y be the original ones digit. Now, this is important, and you have to make sure you know how numbers work. Here's what you can't do. You can't say x, y, and like if it's 54, x, y is 54 now. No, that would be 5 times 4, which is 20. That's not how it works. How would I make 54 out of this? X is a digit. If the 5 is the tens digit, you'd have to say 10 times 5, right? 10x plus that y. 10x plus y would be the original number. Okay? I just want to make sure that you understand that's the original number. Now it says the sum of the digits is 11. So x plus y equals 11. Oh, I don't know if we had to do anything for the... Oh, this will just be the original number. OG number. I thought we had to do something with the equation there. I take it back. When the digits are reversed, the number increases by 27. Oh, okay, yeah, this does matter here. I don't think they mean the sum of the numbers, right? Reversing them doesn't mean anything. So when you reverse this, 10x plus y, when reversed into 10y plus x, okay, they're not equal. They're not equal. In fact, what I should do is say, when I reverse them, 10y plus x, I actually get something that's 27 larger than my original. So like that. Okay, we did need to use that. So 10x plus y, So it makes sense in my head. I want it to make sense in your head as well. So let's do this. Let's first get a standard form appearance of it. I'm going to subtract y over, subtract 10x over. And this is kind of cool. I can divide everything by, actually, let's do this even. Because we're going to get a variable by itself, right? I don't know which one you prefer, but let's subtract y over. Let's subtract x over. And let's divide by 9. We get y equals x plus 3. So my system is x plus y equals 11. Y equals x plus 3. It's a rewrite of my system, but it's one where I now have y by itself. And this one down up here is pretty clean as well. So now it's x plus 3 equals 11. Or 2x plus 3 equals 11. Subtract 3 from both sides and divide both sides by 2. You get x equals 4. Y is x plus 3. 4 plus 3, which is 7. So you get 4 and 7. Find the original number. X is the tens digit, Y is the ones digit, 47. The original number is 47. Now let's double check that one, because we want to make sure everything we did kind of like worked, right? First of all, do the digits add to 11? 4 plus 7 is 11, yes. If I reverse 47 to make 74, is 74 27 more than 47? Yes. Did they want you to guess and check these until you got it right? No. Is it possible? Yes. So you could have checked 1 plus, well, 10 isn't a ones number. You could have checked 29 with 92, 38 with 83, 47 with 74, and 56 with 65. Eventually, you'd find out which one it was. But using algebra and the substitution method, we could also get it as well, guys. And clearly, that's also another way we're looking for it. And guys, that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching. We've solved by substitution, and I hope it's a method that you do quite enjoy. I prefer it more than solving by graphing, but we're going to learn in section 5.3 the elimination method. You might like that even more than substitution method. Most people do, but it depends on the kind of problem setup that we have, especially once we hit like the chapter test. You know, when they just mix review and however it is, it's just a solve, solve, solve. You choose your own methods, and that's something I'm mostly looking forward to by the end of the chapter. We're not quite there yet, only section in. Let's keep moving forward. Thank you so much. Take care. I'm going to see you in the next one.